We are ready for our next speaker, Professor Raesibe Ledwaba. She will be talking to us about architectural variation of lithium manganese trioxide, core shell cathodes during the cycling process. Professor, you have our attention.
A very good afternoon, ladies and gentlemen. Standing before you is Raesibe Ledwaba from the University of Limpopo Materials Modeling Center. And today I will be giving a talk about the architectural variation of our lithium manganese oxide-based core shell cathodes during the charging process. Does this move? Okay. All right, first of all, let me start by acknowledging the CHPC for the tremendous support. I think those of you who were here yesterday noticed that we are the biggest users and we have so much extensive usage. I think I just wanted to demonstrate in the last month when it comes to the minerals processing and the alloy development, they've already used up about 50%. So we'll definitely be requesting for more resources. And we just wanna assure you this is all for a good cause and we thank you for the support. Now moving on to the business of the day. Over here, I just wanted to demonstrate the simple graph of the energy storage demands that we are faced with. So this graph is simplifying that three different cathode materials as well as the energy density that they are able to deliver and the capacity. As we can see, they vary. But the lovely thing is that they also demonstrated in terms of electric vehicle application, the amount of distance that they are able to cover. But in the same sense, we have issues with all of these cathode materials, and we are trying to get in line with the development. So firstly, I want us to look at a very common cathode material, which is the lithium cobalt oxide, which is it's a layered structured cathode material. And the challenge with this material is that it has a very low capacity that it delivers. And this is due to some of the surface reactions and structural instability. On the other hand, we are working on the layered Li2MnO3 cathode material, and this has a potential to deliver about 459 milliamperes hour per gram. But the issue now with our candidate material is that it suffers from irreversible capacity loss, meaning that when it charges and discharges, if it goes at 459, it comes back at around 44% less, so probably around 200, which is something that we do not desire. So in the midst of everything, there are various challenges that are common in electrode materials, and these include structural changes, which are the phase changes demonstrated there. The phase changes, and then these also lead into some form of dissolution of transition metals into the electrolyte. So we also have dendrite growth as well as cracks. These are just a few of the issues that are encountered in lithium-ion batteries. But for the purpose of this talk, I'm going to be only looking into the gray area over there, where we're trying to address the phase change in our cathode material, as well as the dissolution, the ultimate dissolution into the electrolyte. So over here we demonstrate what happens during the phase transition. So basically what happens during the charging process, the lithium ion is removed from its original site and transferred into the anode through the electrolyte into the anode. And normally where there is a vacancy, the lithium that is transported, it leaves with the oxygen, it ignites the oxygen, and this is something we do not desire, because after this we have vacancies. As you can see, these are vacancies formed when we remove the lithium. So what happens is that the manganese, which is this in blue, it now gets attracted to move to this position and forms a tetrahedral coordination instead of an octahedral coordination. And this actually blocks the pathways within the layered cathode materials and starts forming a spinel type structure. So there are several approaches that have been suggested in order to remedy these issues. So some of these are the surface coating, elemental doping, structural design. With structural design, it's a matter of trying to modify the different morphologies. You can work on nanomaterials with different morphologies there. So before we move on to the main business of the day, I just wanted to show that we've attempted elemental doping. So this was a PhD study by Dr. Morashwa. So what she did first, she did the charging process of the pure lithium Li2MnO3 cathode material. And during this, she was able to demonstrate that there is indeed a layer to spinel transformation. And to try and remedy this, she used sodium as a dopant. So basically with sodium, because it has a larger radius, it's able to enhance the interlayer spacing. So it increases the spacing such that the bonds between the manganese and the oxygens are much stronger, and the manganese do not migrate to the lithium sites. So from that study, she was able to identify the optimal sodium concentration, which was 1.25%, and this yielded the lowest activation energy, meaning that this is the energy that is required for the lithium ion migration. And in turn, this works on the diffusion coefficient. So at that 1.25 concentration, we are able to obtain higher diffusion coefficients. So another, another one on elemental doping was an MSc study done by Mamunamani Mphahlele, who's also in the room. And during the study, she used cluster expansion, where she was able to come up with new stable phases. And from the most stable phases, we were able to identify that the band gap was actually modified from the original band gap of the semiconducting material. We're able to reduce the band gap, and the lithium manganese ruthenium oxide system actually has the lowest band gap, and this means that it conducts better than the parent structure. And when we looked into literature, we found that the ruthenium and oxygen actually bond much stronger than the manganese and oxygen. And this gave us even better explanation onto what is happening. So coming to what we're trying to do in the current study, this is from an MSc study by Precious Makubela. She could not be with us, so I'm presenting the talk on her behalf, actually. So what happens is that we decided to coat our materials because we know that the deterioration of the cathode material begins at the surface. So what has been observed in previous studies is that the core shell systems have a superpower, that is, they allow for interdiffusion of elements between the core and the shell instead of elemental loss into the electrolyte. And this can also assist by controlling the thickness of the shell material, where you are able to sustain the structural stability of your cathode material. So over here, I just wanted to show two examples where we have the Li2MnO3 acting as a shell and where it acts as a core material. So when it acts as a shell, the concentration was varied. There are several concentrations that they tried, where they tried the 70%, 30%, and 50%. And it was observed that when the concentration is quite high, it goes back to the issue of irreversible capacity, where about 23% of the capacity is lost. And what was also observed is that the specific capacity of the Li2MnO3 is also compromised at higher temperatures, so they couldn't have it as a shell material. And in terms of having it as a core, there were several good things that came out of it, where it eliminated the oxygen emission and also decreased the initial irreversible capacity loss. But the bad thing is that the charge capacity was then reduced to very low as 178 milliamperes per gram. So in this study, we are looking into a new type of shell material, which is the O2 type material. And this is special in such a way that amongst the different lithium manganese oxide layer structures, it is the only one so far that does not undergo a layer to spinel transition. So we are going for this material to see if it can remedy the issues that I mentioned. In terms of methodology, we designed the core shell using materials design, and the molecular dynamic simulations were carried out using gel poly at CHPC. Then we did a bit of delamination analysis. So this is where we check whether the core and the shell are not dissociating from each other during the cycling process. Then the crucial thing here is that the O2 type structure is not found in nature, so it is a metastable structure that has different staking order as compared to the O3, P3, P2 type structures. So we designed it computationally. And then on the right there, we have the XRDs to confirm the phase. So this is the sodium phase, and then this is the lithium phase. So that way we're able to confirm the O2 type formation. In terms of lattice parameters, we did DFT work on both the core and the shell, and we found that the error margin for our lattice parameters is within 5%, which was a very good agreement. Then we proceeded to do molecular dynamic simulations, and here we're showing the volumetric analysis, during which we found that there was one particular temperature during which a lot of fluctuations were happening, and this was around 900 Kelvin. But we couldn't figure out exactly what is happening, because this was occurring in all the different concentrations from Li 1.9 all the way up to Li 1.1. Then we also analyzed the ionic properties, which are our diffusion coefficients. And in this as well, we saw that there are a lot of fluctuations and couldn't really conclude on the trends of what is happening here. But more importantly is that when we were checking the diffusion coefficients, we found that the concentration that possesses the highest diffusion is the Li1.7 MnO3, which is about 3 nanometers squared per second. Sorry. We then chose as a concentration that we wanted to sample on, and it had to be specifically one that has these kind of fluctuations, because we wanted to see if there was any relationship between the trends in diffusion coefficients and the occupied volume as well as the exposed surface area of our cathode core shell material. And we found that there seems to be some form of relationship, because we have a peak here and then it drops and then it goes up again. And this is exactly what we're seeing with the occupied volume and the exposed surface area of our core shell material. So what we opted to do was to visualize the core shell structures at different temperatures. So basically what we saw is that the shell material remains intact, and then these atoms are coming out from the core, but going back at 900, coming out again at 1.2, then it looks more stable again here. So when we looked at the composition of the core alone, this is the Li2MnO3. In this case, it will be the Li1.8, because we are charging it. So here we have a structure that looks ordered. These are the manganese and oxygen layers. And then this is normally where the lithiums are, so we removed them for clarity. Then at 900, it looks intact again. Then at 1.2, it seems a bit dissociated, with some manganese migrating onto the lithium layer. But the interesting thing is what we saw at 1.5, where we were able to retain the structural integrity again for our core material. And this is something that we really desire, and we are yet to evaluate when it comes to other concentrations. Then here, we wanted to see, we ran our core system alone, and we wanted to see what kind of structural changes it undergoes. And we see that there's gradual, like starting from 300 already, there's manganese migrating into the lithium layer and forming a tetrahedral coordination. And this goes on, and we start seeing some dissociation on our systems. And at 1.5, we see that the structure becomes more disordered. But this one is where it's similar to the one above, where we have the shell, which actually does the interdiffusion between the core and the shell for the atoms. Then we are able to retain our structure. So the final one was now, we've seen the impact of the shell on the structural integrity, but how does it do in terms of diffusion? Because at the end of the day, we still want a material that has suitable capacity and better performance. So what we saw is that there is this is at 300. So from 300, there's a slight dip, and then it increases from there, and then dips again here. This is where the structure was starting to dissociate. But when it comes to the core shell system, we see that where we had that dip in volume, we also have a dip in the diffusion coefficients. And this is sort of a concern for us. So we went back and tried to find out from literature what could be happening. And we found that the stacking fault of our O2 type structure is not always a good thing, especially with the manganese alone. So we saw that in some studies, they actually did transition metal doping to try and improve the cycling performance of the O2 type structure. And another thing, in terms of the temperature, we found that because this is a metastable structure, it's not able to be, it cannot be obtained at temperatures greater than 600. So maybe this can explain what is happening there at 900. But this is some preliminary PhD work, so we'll still look into what is really happening there. So in summary, we noticed that the electrochemical performance depends on the diffusion of atoms, and we have to make sure that we enhance the diffusion of our material, and this will help us so that the capacity is not compromised. So we are looking into doing some elemental doping on our shell material, and also work on the slab thickness of our shell material. So I'd like to thank firstly the NICIs for their computing resources and the opportunity to present this work. I'd also like to thank NRF for funding our students for the master's study, and thank our collaborators at Beijing Espring for all the inputs on this project. Thank my employer, University of Limpopo Materials Modeling Center. I'd also like to thank Precious Makhubela for this wonderful work in absentia, and thank Professor Ngwepe, Dr. Khatwani, Dr. Mrashwa for the doping work, and Ms. Mpahlele. With that, I'd like to thank all of you for your presence and attention. Thank you very much.